So in probability theory, we will see that there are many sequences of random variables, and when we say sequence of random variables, naturally different ideas will come into play. So we should have an idea about the meaning of sequence and some related concepts like convergent sequence or divergent sequence. So right now we will discuss very preliminary things about the sequence of not random variables but sequence of real numbers. So this would be the very basic thing in order to learn probability theory and convergence of sequence of real numbers as well as convergence of random variables. So today we will confine ourselves only to study or first to define what is a sequence, how do we see a sequence, whether it is decreasing or increasing, what is the nature of the sequence when n gets larger, and so on. So right now we will concentrate on some few properties of sequence of real numbers. Sequences 1. So this is the first talk on sequences. The objective of today's talk, we will introduce some concept and definition of a sequence, of course along with some examples, and then we will discuss few important ideas about sequences and results. But first note that today we are going to talk only about the sequences of real numbers. So unless otherwise mentioned, every time we refer to a sequence of real numbers. So first assume that n is a positive integer, and then consider the ordered set of real numbers as a1, a2 and an and so on. So we are talking about a set of infinite numbers actually, and consider this one-to-one correspondence with the set of natural numbers. That means for 1, suppose we have a number a1, for 2 we have a number a2, and for n we have a number an, and so on. That means this is nothing but a one-to-one correspondence between the set of natural numbers or set of positive numbers. So this a1, a2, an are called the real numbers in the sequence. So the formal definition goes like this. We can define a sequence as a function whose domain is the set of all positive integers, that is 1, 2, 3 and so on. And we call this function an infinite sequence, or commonly a sequence of real numbers. The functional value, that is fn, is the nth term of the sequence. Although this is a function, but when we study sequence, we usually denote a sequence by a suffix n or x suffix n or b suffix n, like that. That means basically whenever we have a sequence of real numbers, we can think that it's nothing but a function whose domain is the set of all positive integers. Let us consider a few examples of sequence. How does it look like? First, and very common, we write an equals to 1 by n. That means if we put n equals to 1, we will get 1. If we put n equals to 2, we will get 1 by 2. Putting n equals to 3, we get 1 by 3, and so on. If we put n equals to 100, we will get 1 by 100, and so on. So these are the terms of the sequences that can be obtained by putting n equals to 1, 2, 3, and so on. Clearly, every term in the sequence, that means every number in the sequence, are less than equals to 1. So we can immediately write that all the numbers in the sequence or all the terms in the sequence are positive. So it is basically an less than equals to 1. So we call that the sequence is bounded by 1. Later on we will see some other properties of a bounded sequence. So right now I am going to just giving some examples so that we can have a feel of what a sequence like this. Now one important thing is that as n increases, n is in the denominator, so as n increases, clearly an decreases. So it is clear as n gets larger and larger, the value of n is smaller and smaller. Example is a very simple one. Let's call an equals to 1. That means for every value of n, like n equals to 1, 2, 3, etc., an always takes the value 1. So naturally, as n goes to infinity, an goes to 1. So we can say that limit of an would be 1 when n goes to infinity. It is clear that n goes to infinity, the limit of an would be equals to 1. So we can say that an is convergent and bounded. That means it is converges to 1. Second sequence, we can consider an equals to n square. Now you see, as n gets larger and larger, an gets also larger and larger, and it is not bounded by any fixed number. So as n goes to infinity, naturally we can say that an also goes to infinity. So we can say that an is unbounded and it is divergent. Consider another example. This is very interesting example. n equals to 1 plus minus 1 to the power n into 1 by n. It is clear that as n goes to infinity or n gets larger, the second part, that is minus 1 to the power n into 1 by n, more importantly the part 1 by n, this goes to 0 as n goes to infinity, but 1 remains 1. So we can say that n converges to 1, or limit of n equals to 1 as n goes to infinity. And it is also clear that if we put n equals to 1, this value will be 0. If we put n equals to 2, this value will be 1 plus 1 by 2. So if we again put n equals to 4, this will be 1 plus 1 by 4 and so on. Whatever be the situation, whatever be the value of n, the maximum value or n is always less than 2. It is immediately observed. We can make this bound sharper, but for the moment we can assume that this is always less than 2. So we can say that n is also bounded like the example 1, and it is also converging to 1. Third sequence is very interesting. Consider n equals to just minus 1 to the power n. Now if we put n equals to 1, an takes minus 1. If we put n equals to 2, an equals to 1. Again, if we put n equals to 3, all the odd numbers, an takes the value minus 1, whereas for any even number, an takes the value 1. So n is always bounded, that part is clear, but it is not convergent. So actually, if we just calculate the values of n for different values of n, we see that it will oscillate between minus 1 and plus 1, or in other words, it will take only minus 1 or plus 1 depending on the value of n, or rather depending on whether n is odd even. So naturally this is not convergent. So this gives us an idea of convergent. That means in the limit we can get only one value of an as n goes to infinity, but sometimes it is going to infinity, sometimes it is giving two different values. So what would be the formal definition of convergence? So we say that a sequence an is said to have a limit capital L if for every positive number, let's call it epsilon. So if for every positive number epsilon greater than 0, there exists another positive number n naught, and this n naught might depend on epsilon, but such that modulus of an minus L should be less than epsilon for all n greater than n naught. Now in this case, we also say that the sequence an converges to L, and the notation that we use is limit n goes to infinity, an equals to L, or an tends to L as n goes to infinity, like that. But the basic idea is that as an approaches to L, the difference between an and capital L should be less than any arbitrary positive fixed quantity. And we say that a sequence is divergent if it is not convergent. So the definition of divergence is very simple. So let us consider some few results. Suppose an and bn are two sequences of real numbers, and both the sequences are convergent. That means limit an equals to a as n goes to infinity, and limit n tends to infinity, bn equals to b. Then if we consider another sequence which is sum of these two sequences, that means the nth term of the new sequence is the sum of the nth terms of the two individual sequences, and if we consider their limit, then this limit exists, and this limit would be a plus b. Mathematically we can say that limit n goes to infinity, an plus bn equals to a plus b. Similarly, for any constant c, we can have limit n goes to infinity, c into an equals to c into a. That means as if this c comes outside this limit. Another thing is that limit product of these two sequences, that means the nth term is the product of the new sequence is the product of the nth terms of the individual sequences, and then limit n goes to infinity, an bn equals to just product of the limits of the original sequences, that is a into b. Exactly similarly, we can have another result, limit n goes to infinity, 1 by an equals to 1 by a, but provided n not equals to 0 for every n 1, 2, etc., and a must be not equals to 0. From these four results, we can have many other similar type of results, but which are usually trivial and which can be proved using any of this. So now we are going to prove a few of them, not all. So let's first prove the first result. So it is given that limit n goes to infinity, an equals to a, and limit n goes to infinity, bn equals to b. This means that both the sequences are convergent, and the sequence an converges to a and sequence bn converges to b. I think this part is very clear and very obvious from the given condition. Since an and bn are convergent sequences, then we can immediately say from the definition of convergent sequence that given an epsilon greater than 0, and we fix this epsilon for the moment, there exist two integers, let's say n naught 1 and n naught 2, such that whenever n greater than n naught 1, this will imply modulus of an minus a, there is absolute difference between an and a, is less than epsilon by 2, and whenever n greater than n naught 2, this should imply that absolute difference between Bn and B, that is modulus of Bn minus B, is less than epsilon by 2. But remember one thing, if we want to prove the convergence of the new sequence, which is nothing but an plus bn, we have to find only one integer like this, like n naught 1 or n naught 2. But here, for two different sequences, we have two different integers n naught 1 and n naught 2, and depending on the whether n is greater than those, we get the convergence conditions of sequence an and the sequence bn. So just check n naught equals to maximum of n naught 1 and n naught 2. It is clear that whenever n greater than n naught, that means n must be greater than n naught 1 as well as n greater than n naught 2. So we naturally we can write modulus of an plus bn minus a plus b, that should be less than equals to, by simple law of algebra, modulus of an minus a plus modulus of bn minus b, which is less than epsilon by 2 plus epsilon by 2, because each of this term is less than epsilon by 2. So the sum is equals to epsilon. So ultimately we have that absolute difference between an plus bn and a plus b is less than epsilon. And remember, epsilon is a fixed positive quantity, but it should be very small. But since epsilon is arbitrary, we have the proof immediate. So this satisfies the definition of convergent, and hence we say that an plus bn sequence is convergent, as well as we can say that an plus bn goes to a plus b as n goes to infinity. So this is just application of the definition of a convergent sequence, you can get this proof. Now for the second proof, we proceed exactly similarly. So given every epsilon greater than 0, there exists integers n naught 1 and n naught 2 such that n greater than n naught 1 implies mod of an minus a is less than square root of epsilon. Now epsilon is positive, however small it might be, square root exists. And whenever n greater than n naught 2, this will imply that mod of bn minus b is less than square root of epsilon. Now all we have to show that absolute difference between an bn, that is an into bn, and AB should be less than epsilon. In order to do that, just consider one small kind of identity, a very small result expression. So we can write the difference like an bn minus AB as an minus a multiplied by the quantity bn minus b plus a into bn minus b plus b into an minus a. Now again, following the previous result or previous technique, take n naught equals to maximum of n naught 1 and n naught 2, and using similar type of arguments we can immediately see that the proof is complete, because if we take absolute difference between a and bn minus ab, then this should be less than the absolute difference of three terms, sum of absolute difference of three terms in the right hand side. The first term, that is modulus of an minus a, is less than root over epsilon. Each of the other terms, like modulus of bn minus b, is less than square root of epsilon, and modulus of an minus a is less than square root of epsilon. A and b are assumed to be finite here, so right hand side would be some combination of a, b and square root of epsilon. And since epsilon is arbitrary, each term has a term multiplied by, or kind of product term multiplied by either epsilon or square root of epsilon. Hence the proof is complete. So next thing, we will define one important thing which is known as subsequence. Let me first define what is a subsequence. Suppose we have been given a sequence n, consider another sequence of positive integers as nk, n suffix k. That means nk itself is a sequence, but be a sequence of positive integers. Now remember, an might be or might not be a sequence of positive integers. It should be a sequence of real numbers. It might be fraction, it might be negative, it might be integers as well. But this nk must be a sequence of positive integers such that n1 less than n2 less than n3 and so on. Then the sequence a suffix ni is called a subsequence of an. Just a note is that if we see that a subsequence of n, like a suffix ni converges, then its limit is called subsequential limit of an. So the natural question will arise that is there any relation between the limit of a subsequence of a sequence and the limit of a sequence if it exists? Or is it possible that we can have a few subsequential limits, but can we say immediately that an converges or not? So these kinds of questions we will answer now. First, through examples. Consider the first sequence that I have considered today's talk, like an equals to 1 by n. Now consider two subsequences. One is a to n minus 1, another is a to n. That means first subsequence consists of all the odd numbers of n, and the second subsequence corresponds to all even numbers of n. So the first subsequence means a1 equals to 1, then a3 is 1 by 3, a5 is 1 by 5, and so on. a to n minus 1 would be equals to 1 by 2n minus 1, and the second subsequence a2 equals to 1 by 2, a4 equals to 1 by 4, a6 is 1 by 6, and so on. A to n is 1 by 2n. Note that each of these subsequences converge, and they converge to the same limit, like a1, a3, a5, a to n minus 1 and so on. This subsequence converges to 0 because 1 by 2n minus 1 goes to 0 as n goes to infinity. Similarly, the subsequence a2, a4, a6, a to n, that goes to 0 because 1 by 2n goes to 0 as n goes to infinity. So it is clear that both the subsequences converge, and they converge to the same limit. In this case, the limit is 0. Consider another sequence which is 1 plus minus 1 to the power n, and consider the same two subsequences, like one is with respect to odd numbers of n, another with respect to even numbers of n. It is clear that a1, a3, a to n minus 1 and so on, for all odd numbers of n, an is 0, and for all even numbers of n, an is 2. So if we consider n goes to infinity for the first subsequence, then limit of a to n minus 1, this subsequence is 0, and if we consider the limit of the second subsequence, this would be 1. So both the subsequences converge, but they converge to completely two different limits. So with respect to this observation, one very important result is that an converges to a if and only if every subsequence of an converges to a. Intuitively, this is pretty clear, because consider any subsequence, if it converges to the same limit, then naturally the original sequence should converge to the same limit, that is a. On the other hand, if the original limit converges, then whatever subsequence you can create, it should converge to a, in order that an should be convergent to a. So this thing intuitively is pretty clear. I am not going to prove it mathematically, but the proof is very, very simple, using some argument, using the definition of limits and a few concepts of mathematical analysis. So we have learned what is the meaning of a sequence, how does it look like, and different concepts. So the most important concept related to a sequence is whether a sequence is convergent or not, and how to see, or what is the meaning of convergence of a sequence. So we have learnt already those things. We also have seen a few properties in terms of mostly convergent sequences, as for example, what is the behavior of sum of two sequences when each of the sequence is a convergent sequence. So we have seen many properties, and one interesting thing that we have already learned, that we can create different subsequences of a sequence, and the behavior of the sequence sometimes can be explained in terms of the subsequences, or in other words, if we study different subsequences, we have some idea about the nature of the sequence. As for example, if we somehow find that there exist two subsequences which converges but converges to different limits, then we can immediately say that the original sequence is not convergent. So these are some important but very interesting at the same time properties that one can study about the sequences, and which would be extremely beneficial for future in our future study of sequences of real numbers, and later on sequences of random variables.